All right, so guys, please make sure you try the assignment number 1. Okay, I still have my office hour today, 4:30 to 5:30. If you want to speak about it, no problem. We can talk about it. If you are feeling comfortable, that's great too. Okay, but I will remind you about a deadline, but it's actually set in the PDF instruction. Just make sure you submit in time to claim your credits. And let's now take a quick look on where we are in the course. We are about 2 weeks away from the reading week. Right? So let's take a look where we are, so you can also plan your schedule accordingly. If you look at the semester calendar here, right here. Okay, so we are now on the 29th, lecture number 8. So today, I just want to finish one case study about performing sorting algorithm on the array, namely selection sort, insertion sort. I think that'll be very nicely to say a little bit more about array, like in general, how you can derive the asymptotic upper bound from the array algorithm. And then starting from next Tuesday, we're going to talk about linked list. Okay, so that will be the fresh start. So you can think about next week will be right here, lecture number 9. Okay, so just don't forget, okay, your assignment 1 is actually due next Monday. Right? I'll remind you again, maybe on Sunday. Just please make sure you submit your best attempt. You'll get your full marks. No question to ask. But you got to make sure once I release the solution on Monday, you have to make sure you really follow through the solution if you got any trouble, right? Reach out to me, but just make sure you learn the stuff so you will be okay in the actual programming test. Assignment number 2, so after we cover about 2 lectures on the linked list, I think you should be ready to at least get some basic stuff to be done, right? I'll definitely try to cover as much as I can. So when I release assignment number 2, right here, you will be ready to tackle that, right? So your main job during the reading week definitely will be to complete your assignment number 2. I will also release the programming test 1 guide at least 1 week ahead, right? You can take a look at the guide, know what to be expected, and also I'll give you some practice questions as well. You can definitely try them out. I'll try to host maybe some office hour as well during the reading week. So if you want to reach out to me, ask any questions, you can also do that. So assignment number 2 will be linked list. Your programming test number 1 is going to cover the 2 assignments, right? It's going to be a purely programming test. The style is going to be just identical to the 2 programming assignments. You'll be given JUnit test cases. You can just got to work out exactly how to implement the methods, okay? But I'll give you the guide to say explicitly what you can expect, okay? Any question about the course so far? Anything you want me to clarify? Okay. Yeah, for your lecture role in Aquadet East, I already sent an email to SIT, so I'm hoping that they'll respond, but I'll follow up on them. So we should be okay next Tuesday, okay, to resume our in-person lecture. But please make sure you also follow through the lectures, okay? So I'm going to start this new lecture here, but let's do a very quick recap, right? Of course, the details you have to study, okay? So from Tuesday's lecture, we basically started with some properties about the big O, right? So there were various properties over there. I wouldn't dive into detail. Just remember, these properties are very practical, very important for you to actually understand, right? So just study them and make sure you understand. And then I might just ask you questions related to them in the test or the exam, okay? So for now, I'm just going to skip them. But you know, you have the recording. You got everything, okay? Or you can reach out to me. And then pay special attention to this one here, right? Especially about when you actually want to describe the efficiency or asymptotic upper bound of an algorithm, you want to give the as accurate bound as possible. Otherwise, you might be misleading anybody who's actually listening to your asymptotic upper bound, right? That's really what this page is really trying to say. You want to be very accurate, not just being correct, but also accurate as well, right? Accuracy and also correctness, they're both important, okay? And then over here. And then we just spoke about, just more coding example, right? From Java into asymptotic upper bound, right? You can look at them. I think this one here might be the most complicated one so far about triangular sum. But that one there is not really too bad. You just gotta remember, whenever you got, for example, nested loop, you just have to keep in mind the body of the nested loop right here, the number of times it is going to be executed correspond to all the loop counters involved, about how many combinations we have. In this case, we got I and also J. How do we figure out the explicit number of combinations? The way to do it can be using a table, right? Once you use a table, you can actually figure out the exact pattern, and once you get a table done, you can also go from there about how many iterations, etc. And it turns out this one here is an arithmetic sequence sum, right? That's also something I talk about in the online lecture. All right, so please study this example carefully. But we're going to do something very similar today. Just it's another repetition. Just make sure you really understand. All right. So that's the arithmetic sum. So this is one of the sum formula you have to know. That's the simpler one. Once we get to the tree after the reading week, we got to learn another one, which is the geometric sequence sum. That's something I will review with you as well. That's something that you will have to use for analyzing the tree properties. Okay. All right. And then this is actually already starting from a new lecture about arrays versus linked list. I want to draw your attention to one slide specifically. All right, so you can think about that's what we did on Tuesday, and this is what we're going to do today. And that will start with this one here on Tuesday. Okay, that's what's going to happen. And then arrays over here. All right. So you just want to, before we talk about that particular example, right, you can make sure you understand about why accessing, a particular index in the array is constant time operation. And also, if you want to update a particular index in the array, that's also constant time operation. Whenever you want to just get to one position in the array, it's constant time operation. Okay? However, if you actually want to insert or remove into the array, you don't really want to create any null slots. So that means you're going to involve some shifting operation. The shifting operation typically will involve some loop to actually go through the elements involved. In the worst case, it's going to be linear. Right? So that's the example that we did over here. Right? So that's something we also went over in detail in the lecture. Right? Just make sure you understand about the first for loop and the second for loop, and when will be the worst case for each one of them. Right? That's the detail you want to pay attention to. Okay? Do you guys have any example about this example here? Anything you want me to clarify right now? We're good? Okay, yeah, make sure you study that. All right, please. Okay, and then we basically move on to this slide over here about sorting. So sorting is searching and sorting are the two fundamental problems for computer science or even for software engineering, right? So sorting, we're going to learn about several sorting algorithms. So selection sort, insertion sort is something we'll cover today. And later on, we're going to see merge sort, quick sort. They are more like a recursive algorithm. That's something we'll see and see how we can derive the running time. And after those two, we're going to do one more, which is called heap sort. And that one heavily depends on how we define trees, which we're also going to cover in much detail, right? So these are the 5 sorting algorithms. You got to make sure you kind of know how to apply and also how to trace and also how to analyze their behavior. Okay, that's something we'll cover too. Okay. And sorting problem, we covered that, we defined that, and also about the sorting orders, right? So that's something I also mentioned in the slides. Also make sure you're feeling comfortable about it. For example, the selection sort, insertion sort we talk about today is going to be in the non-descending order. If I change the question to be, let's say, non-ascending order, in which case, how do you modify the algorithm accordingly, right? There's some kind of like creativity you want to have when you study for the material. Always try different variants for the the algorithm or concept that we cover in the class. That's normally how I actually design the question for the test, right? You think about different variants for the concept we cover. Okay, that's good. And then just about talking about sorting order, right? To see which one is more general, which one is more specific, right? You can also look at the lecture. All right, so that's about very quick recap from Tuesday. If you haven't got a chance to study the lecture, you want to do that as soon as you can. Otherwise, you got too much things behind, for the lecture and also for the written test that's going to happen soon, at some point. All right, questions? Okay, all right, awesome. Let's now talk about selection sort and insertion sort, which is fun. Okay. And for today, I also want to make a point. Let me make that explicit, and then we'll dive into these 2 sorting algorithms. All right. Whenever you want to derive the running time, asymptotic upper bound, all right? That's a task. Oh, sorry. Let's say the goal is to derive asymptotic upper bound, big O. Asymptotic upper bound, all right? That's our goal. Of course, eventually, you're going to give me the most accurate big O family, n squared, n cubed, maybe analog it, right, etc. So now here comes the point. What might you be given in order to satisfy the goal? What we did earlier was you might be given Java code, in which case you just analyze line by line or block by block, right? That's one possibility. Okay? That's something we'll do as well today. So possible input in order for you to derive the running time, right? The one we did earlier was maybe some implementation. And in our case, it would be like a Java, right? That's something we did earlier. However, I'm going to start with selection sort, insertion sort, not really giving you the Java code. Instead, what we do is we try to visualize the critical steps for the algorithm. So that should be enough for you to derive the running time, right? So that's something you also want to get used to, okay? That one is more like an abstraction. Abstraction simply means you filter out the implementation detail. Just keep some very high-level concept. Usually that's sufficient for you to derive the asymptotic upper bound. So it's like an abstraction of the implementation. No code. And specifically, you basically have some visualization. And also you simply describe the critical steps. Critical steps. Meaning that these steps are going to dominate the running time eventually. All right, that's something we'll do right away, okay, for you to get some idea. We'll do both for selection sort and insertion sort. I'll show you like two different flavors about how you can analyze the running time based on the abstraction. All right. Another, just one more emphasis. You will see this term here called abstraction very, very often. Not just in this course, maybe for 3101, maybe for other more senior level software engineering courses, okay? Whenever you see the term abstraction, just keep in mind, abstraction, nothing complicated. It simply means you got some simplification of the problem itself. Simple enough, you can still get enough details to solve the problem, okay? It's more like a simplification. Simplification, but still with sufficient details for analysis. Okay, it's also a very important term. I want to really make sure you feel comfortable intuitively. All right? So the way we're going to describe selection sort, insertion sort, we'll give an abstraction of the Java code. All right? Let's start with a selection sort. Guys, I'm just curious. Before today, did you ever work with selection sort, insertion sort before? You have? Okay, maybe some of you. Okay, if no, that's okay. I definitely don't assume. But let's see. It might give you some insights. Okay. Let's start with selection sort. Okay. So you will see that selection sort. So this part here is really the principle over here, right? That's something you can definitely read the slides, but let's now just move on here. I can just repeat again, okay? The name actually comes from the critical step that we need. It's about selection, right? So here, when you say keep selecting in this case the minimum. We have to select the minimum simply because eventually we want to get a non-descending order. You can think about why. Because it's the non-descending order that ultimately we want to achieve for the sorting. But if I changed from non-descending to non-ascending, maybe you want to select something else, right? So think about that one. That's enough hints for you to explore a little bit further yourself, okay? So we're going to keep selecting something, okay? And then, so here I just got already all the arrays drawn for you already over here. Okay, but think about, we just got starting from here. Okay, thinking this way. Okay, I'll make it a little bit more explicit for you. We start with this particular input. You can think about this is the input array that's considered completely unsorted. Unsorted. And the color convention I'm using, I simply use the red for unsorted. As we make some progress for each iteration, you can see that we're going to grow the green area one by one. That means we get more and more sorted. The area for the sorted area in the array is just growing one by one, right? Bigger and bigger. Eventually, we'll get the output right here. eventually we're going to get right here. So this array here, you can think about that one there is the output, completely sorted. And just don't misunderstand, we only got one single array, but I'm just trying to show you different stages of the array, right? Just showing different steps, all right? So how does selection sort really work, okay? So you keep selecting the minimum from the unsorted portion. The first step for the selection sort, in this case, we're given this input. The unsorted portion covers the entire array. So we're going to select the minimum from over here, right? So in that case, let me just write it down first, and then we'll see what it is. So step number 1, right here. So we're going to select the minimum from A at index 0 to A at index 3. Okay? So you can think about starting from A0, all the way to A3. Okay? So from here to here, selecting the minimum. Okay? That one there, obviously, is a linear algorithm, right? If you want to select the minimum from the array, you might have to go all the way to the end to find the minimum, right? So now in this case, we know that the minimum is right here, right? Index 1, right? So this will be the minimum right here. Okay, so this is the minimum that we get, the index for the minimum elements, all right? So now once we know what the minimum is, we're going to use that minimum to grow the sorted area by 1 element. At the moment when we started with, there is no sorted area. Think about it's more like empty. So it will be as if we are trying to insert this element here into the unsorted version, into the empty sorted version, so that we got 1 element there, right? Conceptually. So how do we achieve this, right? The efficient implementation will be, since we know we want the new elements to expand to the sorted area should be at index 0. And we know the minimum is index 1. So we simply do a swap. Okay? The swap goes like this. I know that 1 here should be here. But for the original 3 here, I can simply put it to where 1 belongs to. It's like a swap operation. Okay? So what we do is, we simply say, you can think about this is a destination that we want the minimum to go to. So we simply do a swap. Okay, so once we do the swap, 1 goes to here, and 3 goes to here. And for swap, I'm pretty sure you know how to swap 2 variables, right? You just need some temporary variable to store one of them, and then do the swap. That's something you will see in the actual Java code. But now you just know that swap itself is a constant time operation. It just involves about 2 or 3, I think 3 variable assignments. Okay. All right, so after this particular step, after the swap, now we got 1 and then 3, 4, 2. So now we consider this subarray area with only 1 element to be sorted. And then the rest is considered as unsorted. And the idea is we want to keep going to keep growing the green area until the green area covers the entire array. That's what we want to do. Any question about the first step? Okay, right? Daniel.
You mentioned earlier that selecting the minimum is linear, like we the full elements. Is it possible to do that with recursion?
Yes, definitely. Excuse me. So by selecting the minimum, so first of all, the selection sort algorithm itself is iterative. We simply use a for loop. And as part of the helper method or subroutine for the selection sort, you have to choose the minimum, keep choosing the minimum. So for that subroutine itself, you can definitely try to either implement it recursively or using a loop. It's completely your choice. But even if you try to, say, finding the minimum recursively, it will still boil down into some linear algorithm. You're not going to save any time. Yeah, it will be the same, really. All right. So guys, this first step is the most important because we're just going to repeat, right? I'm going to repeat maybe 1 or 2 more just for you to get a feel. Because once we kind of get our intuition clarified in this example here, what we need to do next step is to generalize it Once we generalize the pattern of some array of length n, we will be able to sum out the running time, right? We haven't seen any code. We don't need to, all right? Okay, let's see step number 2. So this is where we are. You can think about this, what we're going to do, maybe for the second iteration, right? Think that way, okay? So now this area here, we don't need to worry, but we do know that I want to expand this green area by 1 element, but I want to put something over here that's going to be the minimum of this particular unsorted area. That's what I want to do, all right? So what I do is I'm going to select the minimum again. But this time, the area to search for minimum gets a little bit smaller. So here we say select the minimum from, rather than A0, it's going to be from A1 to A3, right? From here all the way to the end. A1 to A3, okay? You can think about starting point is a little bit to the right, but the ending point is still the same. Okay, over here. That's step number 2. Right, what's the minimum? The minimum of this unsorted portion is 2, right here, right? That will be at index 3. Oh, actually, let me be consistent here. So you can think about right here, this is the minimum. And where will be the destination that element should go? It should be exactly 1 element after the current sorted portion. So that should be index 1. So this part over here will be the destination. And the most efficient way to really do it is by swapping, right? So now we're going to swap. Okay, again, it's a swap. So what we do is, you can see the 3 will go here and the 2 will go here, right? It's a swap. So after this step here, you can see, so far we got 1 and 2. That's considered sorted portion, right? And then we keep going, all right? And then you can see the unsorted portion, initially 4 elements, and then 3, and then 2. Let's shrink it down until it's empty, right? Okay, let's now do quickly. Okay, I got 2 more steps. Why don't we just finish that, okay? Okay, from here to here. And then we got select the minimum from A2 to A3. Okay, still to the end. So A3 here remain the same, but it's going to be from A2. Okay, so A2 to A3 minimum is 3 right here. All right, so that one there is the minimum. So this will be the minimum, and then we know that we want to grow this for the portion by 1 element, so it should be here. Right, so that's the destination. Swap. All right. So that one there is going to be another swap. So that's why you see 4 to here and 3 to here, right? So now you can think about this. We are now at the last step because the length of the unsorted portion is simply just 1 element there. Of course, choosing the minimum from there will be trivial. You just choose it, right? It's a constant time operation. So let's now document this last step carefully, okay? Think about this one here. It's the very last step. Okay. So this is the last step where the sorted portion versus the unsorted portion. Unsorted portion is just 1. Sorted portion is n minus 1. In this case, n will be just 4, right? So n minus 1 will be 3, so we got 1, 2, and 3. Okay, I can make it more explicit for you. Think about this part here is really n minus 1. And this part over here is just 1 element. It's a very important special case that tells you this will be the very last step you have to do. All right? So that way, I will just make it complete over here, and then we can generalize it. Okay? So here, this will be the last step. So you still, conceptually, you're choosing the minimum from, basically think about from A3 to A3, you know, just 1 element array. A3 to A3 to A3, okay? So we really have some very nice pattern here that we are progressing, right? iteration by iteration. Okay, that's what we're doing. Any question so far, selection sort? Well, so we're going to generalize it, but let's now answer some question here. Okay. First of all, according to the way it works, the first question, number of steps. You can see here, we got 1 step, we got 2 step, we got 3 step, we got 4 step, right? In this particular example. But now, what if we got an array of length n? How many steps of selection do we need in total? Precisely, according to this. N minus 1? Okay, let's double check. In this case, n is equal to 1, 2, 3, 4. And then we need 1, 2, 3, 4, not n minus 1. Good try. All right. In the last part, actually, you know what? In some way, you can think about this one here, even though it's only one element left in the unsorted portion, but conceptually, we're still thinking about selection. But it's just very trivial selection, right? Maybe that's something you should count as well. All right. So this tells us there's going to be n selections. Thinking this way. Every selection is going to grow the size of the sorted portion by 1. How many elements do you need to grow it? Exactly n elements, right? You got n element to sort, all right? So it will be n to grow the sorted portion size 0 to n. Okay, 0 to 1, 1 to 2, 2 to 3, all the way to n, right? N times, all right? It's a very important question, okay? Okay, second question, and then we are ready to derive it. According to this, when will be the most expensive selection? We got n selections to do. When will be the most expensive? The first one, because unsorted portion is simply the entire array. Symmetrically, the cheapest selection would be actually the last selection, right? Think about this will be the most expensive, and this will be the least expensive, right? So it's really decreasing, okay? Also, another fact, cost of selections, indeed decreasing. All right, having these two in mind, we can now try to generalize it. And for the selection sort, I'll try to just draw some diagram to generalize it. That's one flavor you guys can try. Okay, let's try that. So what I do is, let me start with the input. So the input here is simply of size n. And in the beginning, everything is unsorted. We'll start with this. All right? And then eventually, what we want to have is have the same array, the same length, size n. However, everything should be sorted, right? From the input to the output. Big picture. Okay, let's just try a few steps. Okay. After the first step, what we have is the sorted portion is going to be just 1. Unsorted portion is just going to be n minus 1. Okay, so we got n minus 1 over here, and then we got 1 here. Okay, just the size. Okay, and then let's just do a few more. Okay, and then the second step is going to grow the size to 2. So let's think about this one here will be size 2, and this will be n minus 2. So 2 here, and also n minus 2 right here. All right? So far so good? Okay, the pattern will continue. And the very last step, starting point, will be we still got an array of size n. But now this time, what will be the size for sorted portion? N minus 1, exactly. All right, thank you. N minus 1, and right here. Okay, that'll be 1. All right. So right here, also right here. Okay? All right. You can think about this diagram here. It's basically the same, but we're just making it more general. So it can be for any length of the array. It can be 10, can be 20, can be 100. All right. And then let's now try to see the running time. There are basically two critical steps for each iteration, right? When I want to go from here to here, basically, number one, I got to select the minimum. And number two, I got to swap, all right? So you can think about from here to here, from here to here. Let's see here. Okay, from here to here, I got selection. Also, I got swap. Okay, let's figure out right away. What will be the cost for the selection? N, right? Because the size is n, right? Maximum. Good, thank you. And then for the swap, of course, you can count exactly how many primitive operations are there. You can do that, but it's going to be constant. Just some variable decoration, maybe some variable assignments, right? So I'll put swap just 1 here. Okay? But you will see exactly how to do the swap when I show you the Java code. And then if you try to do the next step right here, we still got the critical steps, selection, and also swap. Swap remains to be 1. But now selection is going to be decreasing the size a bit, n minus 1, right? Because you are choosing the minimum from right here, n minus 1. Okay, keep going. And then when we go for the last step, that would be still involving selection and also swap. Swap will still remain to be 1. But now selection will be just 1 because only got 1 element to choose from conceptually, right? Just 1. All right, so now we got enough information about the running time. We just need to make sure we can sum up all these numbers. Before that, let me say one more thing. About the number of steps. Step number 1, step number 2, all the way to step number n. After step number 1, we got 1 element in the sorted portion. After 2 steps, we got 2 elements there. After n steps, we'll get exactly n elements in the sorted portion, right? Etc. Okay. So think about this is step number 1. This one here is step number 2. And this will be step number n. Right? We got n steps in total. And we want to add them up. All right. And let's look at it separately. This part here, 1, 1, 1. It's always 1. It's basically just n times 1, right? Just for the swap itself. We're going to do the swap n times. On the other hand, if you look at the n minus 1, all the way down to 1. Does it seem familiar? It's an arithmetic sequence, right? The common difference is simply just minus 1. I go for n minus 1, n minus 2, all the way down to 1. All right? So let's now try to do a little bit of summation together. Okay? Okay, we don't need this anymore. Okay? So all we are doing here is just to make sure we set up the context for visualization and we understand what a critical step should look like. And now we can add them up. So let's now do this. It's going to be the big O of, okay? Let's now separate the concern. One is about the swap. Every swap is going to be 1, okay? This will be the swap. And we do exactly n swap. Multiply by n. So this will be, n will be how many steps we got to do. Each step involves 1 swap. Okay, and then let's talk about selection. Think about this part here is going to be about the cost for the selection, right? And it's going to be n plus n minus 1 plus all the way to 1. Okay. So we got is n plus n minus 1 plus all the way down to, right? So you can say this here, just to make some notes, this will be the first selection. This will be the last selection, or you can think about it as the nth selection. All right? And then we'll try to add them up together. Just for this part here, right? The formula here, right? As we mentioned in the last lecture, is going to be the beginning plus the end, multiply number of turns divided by 2, right? Beginning will be n here, the end will be here. N plus 1. Multiply how many turns? From 1 to n? N turns. Thank you. And then divided by 2. Okay? I would say in the test or in the exam, up to here will be good enough. You don't really have to calculate exactly because we know it's big of n squared. If we can see you deriving up to here, we're convinced you understand the stuff. Right? So this one here is going to be basically just n squared. This part here. Okay? Think about it's simply just n squared. Okay? Think about this part here is big of n squared. And apparently, n squared is going to dominate n. Drop the lower term. We got n squared. All right? And eventually, we're going to see big O of n squared. It's a very important conclusion, right? So we're basically saying that selection sort is a quadratic sorting algorithm. Definitely not linear, more costly than linear strictly, also more costly than n log n, selection sort. Okay? And we haven't seen any Java code. We don't need to. Okay? All right, question. Feeling comfortable? Yeah, Daniel.
You mentioned at the beginning of the class that when we try to make sure that we keep enough details to solve the problem. Would this be a simple enough breakdown?
Oh, absolutely. So basically, once you see the Java code, okay, I'll show you very quickly. I think we can take a break a little bit earlier today. Okay, I think so. This is the abstraction, right? The simplification. On the other hand, another flavor, another version you can do. For example, Java code, right here. All right. So after the break, at some point we can try to look at the code itself and try to derive the running time, like how we did it earlier. Right. So this one here is the absolute 100% details. Right? We didn't really mention exactly how you do the variable swapping, which is simply show you visually how to do swap. And we simply say swap is just a constant time operation, right? So yes, indeed. So this will be enough information for us to know to approximate the running time. Yeah. All right, why don't we? All right, so let's now move on to insertion sort. But on the slides, on slide number 5 about selection sort, you will also see the Java code. So I'm going to talk about Java code maybe after insertion sort. I'll give you some idea about how you can figure out the running time. We'll do the exercise again, but I do have some exercises for you guys as well. That's something I will let you know at the end. Okay. Selection sort n squared. Okay, and then insertion sort. Okay, insertion sort is done in a very similar way, but the dominating operation is going to be insertion. That's really where the name actually comes from, insertion. We'll see exactly how that can be done. But we're going to start with certain sorted portion, almost empty in the beginning, and then we're going to grow it for each iteration. And then we're going to see how we can derive the running time just by considering the abstraction, just the critical steps, without having to see the code. Okay, that's something we'll do. So let's now move on to insertion sort right here. Right, we'll do something very similar. I already got all the arrays there. Okay, and of course, insertion sort. Okay, so here I say just getting. It's not really selecting. Getting simply means just go to a particular index in the array. Right? You're always getting somewhere without having to make any decision. Okay? But it's going to be inserting. Okay? So this will be the dominating action. So what I want to, first of all, when you want to get the first elements from somewhere, it's just big O of 1. Right? It's not really like selecting. That's why I try to avoid using the word selecting. Okay? And the most critical action there is going to be inserting. Okay? Inserting here is going to magically, well, nicely, correspond to the lecture we studied on Tuesday about inserting into the array. All right, so that's why I can talk about that example earlier before I talk about insertion sort, right? So I'm going to briefly mention that, but the details you have to see how exactly insertion can be done, right? That will give you some nice inspiration. Okay, just keep in mind, it's kind of related. Let's get back to the insertion sort. Okay. So the idea is, in this way, in this particular algorithm, because I was trying to make the visualization more corresponding to the code that you're going to see later. So here we start with the sorted portion with size just 1 rather than empty. Right? It doesn't really make a difference asymptotically. Right? So let's say we're given some input. Again, so think about this one here is the input. This one here is the input. Okay, and this one here, it will be the output, which is completely sorted. The subtle difference is the input here has one element. The sorted portion is already has already one element in it, whereas in the selection sort in the beginning, sorted portion is empty, right? Subtlety, right? Just make it a little bit more corresponding to the code. But if you really prefer to have the sorted portion to be empty, you can do that exercise as well. It's gonna be the same. Okay. So we got input and we got output, right? So now the first part, getting the first element. This is the sorted portion. What we do is we try to get the first elements. Getting there, simply constant operation. Once we get there, we are trying to insert this particular element here into this sorted portion area. In this case, we might have to either insert it to the left or the right of that particular elements that's in the sorted area. So in general, if you want to insert it into a particular sub-array, you have to somehow use a loop to see where exactly is the right position to insert, right? That's something we kind of covered about inserting last time. But just let's say for this one here. For us to get, first of all, this is the element that we get. Okay? And then we want to insert this element here into this particular portion. Apparently, we should insert to the left of 3, because 1 is less than 3. So after inserting, we got 1 and 3. Okay? So here, I'm not really saying we are swapping. It's actually more complicated than the swapping, as we'll see. Because somehow, when the area of the sorted portion is bigger, you may have to insert somewhere in the middle. So it's not exactly swapping, not exactly. Okay? So the first step, right here, is going to be right here. You want to insert the element we get, which is from A1. Right? And after inserting, we got the sorted area grown to size 2. So we got 1 and 3. And the unsorted portion shrunk by 2. Shrunk into 2 elements. Right? And then next step. Now we are trying to get the first element from the unsorted portion, which will be this one here. Just choosing it, right? Just getting it. And then now we have to decide if we want to insert 4 into this sorted portion, right? So where should we insert that into? Should be right after 3, right? Because 4 is strictly larger than 3, right? We should insert after that, all right? So what we do is, in this second step here, we are trying to insert A2, okay? So A2 over here is the element we get from the unsorted portion, all right? So now we are reaching really the beginning of the last step, all right? So that last step is very similar layout, okay? Let's now remind ourselves. You can think about right here, this part here. This is the sorted portion, which is of size exactly n minus 1. And then the unsorted portion right here is of size just 1. So what we do is we try to pick or get, right? We try to get the only element that's in the unsorted portion. So what do we do in the last step? We'll try to insert 2 over here into this sorted portion in a way that's going to make the larger sorted portion remains to be sorted, right? So now 2 should not go here, right? And 2 should exactly go here, 2. What does that mean? If 2 has to go into this one here, this position here, that means 3 and 4 should somehow be shifted to the right by 1 position. That shifted to the right position, in the worst case, can cause linear time, right? That's really about the inserting that we did last time, all right? So you can make a note right here. you can think about the 3 here used to be at index 1 is now at index 2. And the 4 that used to be at index 2 is now going to be index 3. All right? And then the 2 that we try to insert is now here. And then the 1 that used to be there remain unchanged. That's exactly the layout that we talked about on Tuesday, right? You want to really draw the connection between these two. All right? So that'll be the last step. Okay? But we're going to generalize it. So that one there is actually we try to insert A3. Okay, you can think about A3 over here is really the last elements. Last element that happen to be just unsorted conceptually. All right. All right. So now I'm going to show you a slightly different way to really try to count the running time. Okay. I'm going to use a table. Just before that, let's clarify one important concept about inserting. All right. So you can think about this part here is more like a review about what we did on Tuesday about inserting. Okay. Let me lay it out. Okay. So we are really talking about what's the worst case. For insertion. Let's see. For example, you can see here, when I actually try to insert this element into here, right? It should be 1 followed by 2 and then 3 and 4. A cheaper one would be, well, if this, let's say, for example, it happened to be 6. In that way, I don't need to do any shift. Apparently, that's cheaper operation. I can simply just let 6 remain here. There's no shifting to the right involved, right? But I'm talking about the worst case. The worst case would be, let's say this one here, rather than 2, let's say it's -1, let's say. If that's -1, that means it should really go here, -1, before everything else. That means 1 should be shifted to here, 3 should be shifted to here, and 4 should be shifted to there, right? So that'll be the worst case, right? Just sounds very quick hand waving. But let's now visualize it, okay? Let's say in general we're given something like this. Let's say we got our array over here. And then let's say this part here currently is the sorted portion. And this part here is the unsorted portion. Number 1, we pick or we get the element that's leftmost in the unsorted portion. So what we do is we try to get it right here. Okay, we try to get it. Okay, think about we try to get this element here, and then what we are trying to do is we are trying to insert this element into the green area, and the area is going to be grown into of size the area +1. But where should this orange element go? What will be the worst case? Right? The worst case would be if the orange one happened to be just the minimum elements. That's kind of smaller than everything in the green. In that way, we got to shift everything to the right by 1 position. Okay. Worst case, it is smaller than all elements in the green area. Okay. I know it's not really a complete English sentence, but you see my point, right? If the orange one we're trying to insert will happen to be the leftmost in the sorted portion after the expansion, right? Okay, let's visualize it. So what's going to happen is we still got an array of the same size. And then, now be careful, the green area is actually going to be grown. Right here, right? Just 1 element more. And this orange element here will just become the very first element. Right here. And this portion here corresponds to exactly this old entire sorted portion before the insertion. Okay? So think about this part here. This one here. Okay? That means we've got to shift the whole block to the right by one position. So this will involve shifting the entire old sorted portion by one position. Okay, let's say, for example, if this is actually of size I, the cost will be just I, because you're going to run a loop to shift all the I element to the right by one position, right? Okay, it's going to be the big O of I. Okay, the I here is just about how large that sorted portion is. Any question about this critical visualization here? Once we know this one here, we can now do a table and then we sum up. Okay. All right, let's now try to draw the table. Okay, I'll try to make it a little bit smaller, right? Because I do need some space. Okay. So we're going to talk about like a step, first of all. How many steps do we have in this case? Given that the starting sorted portion is not empty, it's actually of element 1. Would you like to give it a try? I agree, exactly, n minus 1. That's great, right? So you can think about, we basically go, if let's say here, 1, 2, and 3. 3 steps, which is exactly 1, 2, 3, 4 for element minus 1. Right? It's a some subtlety there, right? Okay, so we got basically step number 1, and then 2, and then 3, all the way to n minus 1. Okay, we got these steps. But let's now try to enumerate a few, just to see the pattern. And of course, we're going to get, right? It will be the get. So index 1, index 2, all the way to the last index. Agree? Okay. So going to get A at index 1, A at index 2, A at index 3, all the way to 8 at index n minus 1, which makes sense. A at length minus 1 will be exactly the last elements in the array, right? That will be the last one to pick or get from the unsorted portion and then insert into the sorted portion. That's the last step. All right, next column. We got to figure out, in order to see what the cost is for the insertion, we want to see how large the sorted portion is, right? The sorted portion here of I here, initially could be just 1. And it will be 2, and then 3, right? So insertion is really having increasing cost as we go. So now if you think about selection sort, selection got decreasing cost. There's a symmetry over here, all right? So we can say here, size of the sorted portion. Initially will be just 1, and then 2, all the way to n minus 1, right? You can see this will be the last one. So it will be 1, and then 2, and then 3, all the way to n minus 1. And the last column, very important, right? The last column here is going to depend on our understanding about here. Depending on how large the sorted portion is currently, the worst case will be the one we try to get and insert happens to be the minimum in the new area. In that case, we're going to shift the entire block to the right by one position. Okay? So that means it's going to correspond to just I. Okay? I here. So when the size is actually 1, the cost will just be 1. Okay, let me just write it down here. So that will be the max cost for insert. And when the sorted portion size is actually 2, it will be 2. When it is 3, it will be 3. Simply means we got to shift all the 3 elements to the right by one position. Right? And then go all the way to, if the sorted portion in the last step is simply n minus 1, maybe you got to shift everything to the right. That will be just n minus 1. And one thing also important, I think that's also worth mentioning. That means the insertion cost, the cost of insertions will be increasing. That's another very important insight for you to see. All right, we got a table, and we can now sum up and get a running time. You can think about there are two steps over here. One is about getting, which will be constant. And also we got insertion, which will be increasing. So we're going to split them, right? Let's now remove this one here. Okay, let's now do similar summation. I'll get n minus 1 step. We go right here. Let's start with just getting. So this will be to get. For example, getting this one, etc. And we got exactly n minus 1 steps. So this will be the number of steps, okay, plus. You can think about the get in insertion sort is like the swap in the selection sort, similar, okay, but different purposes. And then how about the insertion itself? And now because that's increasing cost, so what we get is we're going to sum up the cost right here. It's going to be 1 plus 2 plus 3 plus all the way to n minus 1. And this one here, we can do it right away here. This will be insertions. Arithmetic sequence, right? Beginning plus the end, 1 plus n minus 1. Multiply, how many turns? n minus 1, right? n minus 1 steps, okay. Divided by 2. Okay, that'll be enough. We don't need to simplify any further. That one there is going to be n squared. So this one here is just going to be, obviously, big O of n squared. And you can see the n squared is going to dominate this one, lower term, drop. Okay. So what we get is, we got big O of n squared. So far, we have tried both the selection sort and insertion sort just by considering their critical steps. And then we conclude that they're both, you can think about they're equally efficient asymptotically. They're both quadratic. Which one to choose is completely up to you, right? So it wouldn't make a difference when the input size gets towards infinity, right? N squared and n squared right here, all right? All right, question? All good? Okay. All right, so please review about these details because question can come from here, right? I can definitely test you about conceptual or maybe the counting, etc. There are many things I can ask you. Just make sure you study the details, right? Always pay attention to detail. Okay, so there will be some exercise I can suggest, maybe a little bit later. Okay, let's just move on. I got about 18 minutes. We can do a little bit more. Okay. So if you go to the slides number 6, so that's also the Java code. You can also take a look. I'll show you briefly. Okay. And that one there is going to tell you n squared, just what we did. Okay. So this is very important. Okay. Important exercise for you. Okay. So I actually, this will be slide number 7, but I'll show you what I mean. We got a Java code. I also gave you the code. I believe it's on the lecture site. Let me double check. Okay. If you actually go to, I didn't. Okay, I'll see if I got a code. If no, you can just use the slide version. That's fine. Okay. So we got a Java solution to selection sort, and also we got a Java version for insertion sort, right? We're going to do the asymptotic upper bound for one of them. We'll do that. But exercise for you guys, for selection sort, and also for insertion sort, tracing is also an important exercise I would expect you to do. All right. So what you guys should do is I already lay out everything nice, kind of cleanly for you. Okay. Let's say for insertion sort, you're just going to trace, let's say this particular array according to the algorithm to see how the array eventually is going to be sorted. Right. So you're going to start with the loop counter over here, starting from 0, etc. Right. So I can lay out why it should really fill in. Okay. You'll do the similar tracing exercise for insertion sort as well. And try it out first, and then you will see that if you really want to go over some video solution with me, I also got a link for the video right here. I kind of show you about how to do it on the paper, and also I show you briefly how to do it in Eclipse as well. So these 3 links on the slides is also very critical, right? We wouldn't have time to cover that in the class. That's something I would expect you guys to do. All right, spend some time over the weekend while the idea is still fresh in your mind, okay? So that'll be the tracing exercise, okay? So you gotta make sure you trace for insertion sort. And also you will trace for insertion sort, selection sort, insertion sort, okay? Okay, right here. Okay, I'll put it down here. Good. But I want to talk about maybe just this selection sort Java, right? So now I want to show you another extreme. So let's say you're really given the Java code for selection sort. Now, how do you derive the running time? Okay. Number one, in order for you to derive the running time, you don't necessarily have to understand the complete details about every line. You can just go line by line and do the analysis. Okay. So just to start with, let me emphasize the point. You don't really need to. Not necessary to understand the logic of algorithm if your goal is just to derive the asymptotic upper bound. You can simply just look at the code structure and then derive it. Right? We do things separately. If you really want to understand about the logic for the code, you got to do the tracing exercise that we kind of showed to you. Right? All right, just for this one here. Okay. Why don't you guys take a quick look on the selection sort? Again, you don't need to understand the logic completely. Right? Look at the code structure. See the loop counter, see how many nested level do you have, and also about how many times each line is going to be executed, right? Plan something, and that we'll go over, okay? This one here, very similar to triangular sum, actually, but it's not exactly the same, similar. Just I'll pause for 1 minute, you guys can take a look, and then we're going to go over. Especially, a little hint, if I may. Think about how many times line number 3 is going to be executed. How many times line number 5 will be executed. Also, how many times the block consisting of line number 6 to line number 8 will be executed. So these are the 3 questions you want to answer first to yourself before you can start deriving. Okay, one more moment, and then we'll get started. Okay. Okay, so let's now take a look. Right? Let me just talk about them line by line. Okay. First of all, the indentation. This is the outer loop. That means this particular indented block over here is the body of this outer for loop. Agree? Accordingly, this line here and also this block over here, this is like a phase number 1 for outer loop. This is like a last phase for the outer loop. The number of times they will be executed only depends on how many times the outer loop is going to iterate, which only depends on the value of I. All right. So now let's write it down. This one here and this one here. So number of executions depends on the value of I right here. All right. Questions? It's okay? It's critical, right? All right, what about line number 5? You can see that line number 5 is indented inside the second for loop. So that means the number of times this is going to be executed depends on both the I and j, the loop counters, combination. So that means we've got to do something similar to triangular sum to draw the table. Let's write this down. All right, so here I'm just going to make a quick annotation here. The number of execution for line number 5 depends on the values of I and j combination. Each combination of I and j is going to correspond to one single execution for line number 5. Individually, they cost only 1, right? So this block, this line here, just constant. It's just about variable assignments. This one here, line number 5, is also cost 1, right? That one there, just about array indexing, relational operation, variable assignment, right? And finally, line number 6 to line number 8. That one there is really doing the swap, right? If you look at the swap a little bit more closely, you don't need to, but you got array indexing here, you got variable assignment, etc. Constant, right? Overall. That one there is also constant, just 1. So we just need to figure out the patterns for I and j. That's all we need to do. Let's draw the table as we did for the triangular sum. So for I, I'm going to use purple. For j, let me use green. These two. Okay. Let's first of all start with the value of I. It's going to be from 0 all the way up to and including n minus 2. Because you got less than or equal to, right? Not less than. So what we get is we got 0, we got 1, we got 2, all the way to n minus 2. So these are the values of I corresponding to all the iterations for the outer loop. And we can count accordingly about how many iterations. It's really the interval between 0 and n minus 2, right? Our little formula tells us we can do n minus 2 minus 0 plus 1. N minus 1 iterations, precisely. N minus 1. We're okay with this? Just for the outer loop, just for I alone. And then the j value depends on the I value. As you can see here, j initially just to be I, and then go all the way up to and including n minus 1. Not difficult, right? We did something very similar in the triangular sum. Let's do it. So for that one there, j will be, starting value should be just I. 0, 1, 2, all the way to n minus 1. When I is equal to 1, j will start accordingly from 1. And then 2, all the way to n minus 1. When I is equal to 2, j will start accordingly from 2, all the way to n minus 1. When the last value of I is n minus 2. In that way, j will start with n minus 2, right? N minus 2, and then all the way up to n minus 1, which will be just next number, right? Good. If you're able to get to this point, that's very nice. But the most critical step is to interpret the table. We want to see how many combinations. One combination 0, 0, another combination 0, 1, and then we got also 0, 2. Right? How many exactly? So what we do is, for this one here, we got between 0 and n minus 1. For this one here, we got between 1 and n minus 1, right? I'm just talking about the beginning all the way to the end. And beginning all the way to the end. As you can see, the interval is shrinking. Beginning also to the end, right here. That will be from 2 to n minus 1. And beginning to the end. So that one there will be from n minus 2 to n minus 1. Right? Let's see the size for the interval. What's the size here? N minus 1 and n plus 1? N. N minus 1 minus 0 plus 1. So this one here is going to give you n. And this one here is going to give you n minus 1. Right? You can double check. N minus 1, and then it's going to get decreasing. And n minus 2 all the way to, what's this? What's the size? 2, right? Exactly, right? Double check the math, right? If you got any trouble, let me know. I can work it out with you. It is indeed, again, arithmetic sequence. All right? Now we got all the information we need. Let's now gather them together, do the big O. Okay? Let's do it. So what we do is, we can now do big O. Let's now talk about this line here. Line number 3. Each execution will be cost 1. How many? Depends on I, which would be n minus 1. N minus 1 multiplied by 1. So the 1 here really is about line number 2. And this will be the value for I. And similarly, we can also do n minus 1 multiplied by 1. And I'm just writing them separately, right? Yeah, just make sure it's complete. And this one here will be line number 6 to line number 8, similar. Line number 6 to line number 8. And we also got I iterations. Well, sorry, not I iteration. The iteration corresponds to I value. That's what I meant to say. And then, what we do is, we're now going to sum up. Okay. I'm running out of space, so I'll just change to a new line. Plus, so this part here. This part here is going to be about how many times line number 5 is going to be executed. So line number 5 will be just 1. This will be line number 5. And how many times? We got n plus n minus 1 all the way down to 2. N plus n minus 1 plus n minus 2 plus all the way down to 2. Right? We've been doing this sequence for the 3rd time already today, right? So hopefully you'll get more and more comfortable with it. This one here, again, let's now consider it separately. Beginning plus the end multiply how many terms? N minus 1, right? Here you can see how many terms do we have? N minus 1, corresponding to how many values we have here. All right, double check. So that would be n minus 1 divided by 2. All right, that would be sufficient. Okay, don't need to simplify any further. That one there apparently is going to be n times n, big O of n squared. So that would mean this term here, n squared, is going to dominate over the lower term right here. So the dominating factor is really about how many times this one gets executed. This one here and this one here simply correspond to lower term. We can drop it for approximation. So that would be just big O of n squared. And the important thing is to see this result over here is consistent with the selection sort we did earlier. You can see either we're given the Java code or we're only going to visualize the critical steps. They should give us the consistent result. Okay. I got about 2 minutes. How about do one more thing very quickly? But it's more like a brainstorming, or like a little bit brain teaser. How about that? All right, make sure you, this will be exercise for you to figure out the asymptotic upper bound for insertion sort. I'll put exercise over here. Okay, and tracing as well. Okay, this one quickly. Okay, I'll explain what's going on here. Think about it. We can go over the solution very quickly on Tuesday in the beginning. Okay, so here's one thing. For selection sort, we talk about the cost of selection being increasing. For insertion sort, the cost is decreasing. So now we are thinking that, can we try to have a new sorting algorithm, like a hybrid one? It is going to try to do, let's say this. Let's say the array looks like this. Let's say the array size is n. So now for the first half, n over 2, and the second half, n over 2. We are trying to do maybe just the insertion sort for the first half. And then we try to do selection sort in the second half. Insertion sort for exactly n over 2 elements. And then we do the remaining n over 2 elements by selection sort, hoping that the decreasing cost is going to give us the maximum benefits. That's a hybrid algorithm. Now here's a question, okay? Part A. What's going to be the running time for the hybrid algorithm? Part B. Can you show the step to derive it just by using some diagram? Because I don't give you any code, right? Number 2. Number 3, is there any particular input format that this hybrid algorithm is going to rely on? Let me write down A, B, and C. Think about it over the weekend, and then we can go over it. Give me 1 minute. I'll write it down, okay? Please. Okay, so actually it's already there. I'll go over it quickly. So the first question here, will this new algorithm, especially, is it going to be worse, the same, or better? Number 2, justify your answer. Maybe using some diagram right here. I already drew that for you. Number 3, is there any particular, we call precondition, like a assumption we have to make on the input array in order to perform this hybrid sorting algorithm, right? So these are the 3 parts. Think about it. This can well be some format for the exam or for the written test. Try to practice. And then we'll do the solution on Tuesday. Thank you so much. I'll see you next week.